Solutions. Solvent properties of water. The properties of water. Polarity of water molecules. The polarity of water molecules is one of the most critical factors contributing to water roles as a universal solvent. As you know that water is actually a universal solvent, so its polarity has the main role in the water solvent. First of all, this polarity arises from both the molecular structure of water and the difference in the electronegativity between its constituent atoms, hydrogen and oxygen, which is basically the hydrogen bond. Molecular structure of water. A water molecule H2 consists of two hydrogen atom covalently bonded to an oxygen. So there is two hydrogen atom covalently bonded to one oxygen atom. While the bonds are covalent sharing electron, the sharing is not equal to oxygen due to oxygen's high electronegativity. What is electronegativity? Electronegativity is basically the ability of an atom to attract electron in a bond. Oxygen has electronegativity of 3.44, while hydrogen has electronegativity of 2.20. So as a result, the shared electron are pulled closer to the oxygen atom, giving it a partial negative charge. So the oxygen become a partial negative charge, while the hydrogen become a partial positive charge. This looks like this. For example, let's say hydrogen partial positive and oxygen partial negative. This uneven distribution of charges creates a dipole moment within the molecule, which is also known as hydrogen bond. Bend geometry and dipole moment. The geometry of water molecule further enhances its polarity due to the lone pair. Because oxygen has lone pairs, water adopts a bent shape with an angle of 104 instead of linear. So instead of linear, it has a bent shape because it has got lone pairs on oxygen. This bend structure means that the two OH bond dipoles do not cancel each other out, and the result in a molecule with a distinct positive side and a negative side, leading to a net dipole moment of 1.85 dB. The presence of this dipole moment makes water a polar molecule, which is essential for its interaction with other charged and polar substances. Hydrogen bond formation in the water. The partial positive charge on hydrogen and allows water molecule to form hydrogen bonds with the lone pairs on oxygen atom of neighboring water molecules. What is hydrogen bonding? Hydrogen bonding is basically the bonding of hydrogen atom of one molecule with the most electronegative atom of another molecule. So the hydrogen of one water molecule bonds with the oxygen of another bond molecule. Each water molecule can form up to 4 hydrogen bonds. Remember, each water molecule can mm, form up to 4 hydrogen bonds, leading to high cohesion and solvent capabilities. The polar nature enables water to interact with and dissolve with polar molecules and ionic compounds. Surface tension and cohesion. Water's polarity lead to strong intermolecular forces, giving it high surface tension. This is hydrogen bonding. As you can see here, this is one water molecule. It can easily bond to 3 another water molecule. This dotted line, actually, this dotted line is basically a hydrogen bond because intermolecular forces is always represented by dotted lines. Hydrogen bonding. What is hydrogen bonding now? The hydrogen bonding is a type of strong dipole-dipole interaction that occurs when a hydrogen atom, so when a hydrogen atom covalently bonded to an electronegative atom such as oxygen, nitrogen, or fluorine experiences an attraction to another electronegative atom nearby in case of H2O. So the hydrogen atom partial positive or covalently bonded to oxygen. The oxygen partial negative being highly electronegative pulls shared electron closer, creating a partial negative charge on oxygen and partial positive charge on hydrogen. So this will lead to an electrostatic attraction between partial positive hydrogen of one water molecule and the partial negative oxygen of another, forming a hydrogen bond. Number 2. Structure and formation of hydrogen bonds in water. A single water molecule can form up to 4 hydrogen bonds. 2 through its hydrogen atoms acting on donor, while 2 through the lone pairs on oxygen acting as acceptor. So these hydrogen bonds result in a network-like structure in liquid water and a more open hexagonal lattice in ice. In liquid water, hydrogen bonds are constantly forming and breaking due to molecular motion, creating a dynamic but cohesive liquid. Role of hydrogen bonding in solving properties. Hydrogen bonding enables water to dissolve many polar and non-polar ionic compounds. Water surround an ionic compound, let's say for example NaCl, it will break it down to two Na plus and Cl minus, partial positive on Na and partial negative on Cl. Dissolving ionic compounds. Water is an exceptional solvent for ionic compounds due to its polar nature. So water is polar and ability for form hydration shells around ions. The process of dissolving an ionic compound such as sodium chloride involves the breakdown of the ionic lattice and the stabilization of free ions in solution. So the NaCl breakdown and it stabilizes the system. Now, structure of ionic compounds. Ionic compounds are made up of a three-dimensional crystal lattice consisting of alternating positively charged cation and negatively charged anion. These ions are held together by strong electrostatic force ionic bond, which gives ionic compounds their solid crystalline structure. Example in NaCl, Na plus, and Cl minus ions are arranged in a repeating lattice bound by strong attractive forces. Role of water. Role of water's polarity. Water is a polar solvent, meaning it has regions of partial positive and partial negative charges. The oxygen is partial positive while the hydrogen is partial negative. This polarity allows water molecules to interact strongly with both positive and negative ions on an ionic compound. The dissolution process. The process of dissolving an ionic compound in water involves several key steps. Number one, ion-dipole interactions. So when an ionic compound placed in water, the polar molecules are attracted to the positively charged ion. So the cation, the Na, are attracted to the oxygen side, to the partial negative side, and the anion, the chlorine, partial negative, are attracted to the hydrogen side. These interactions are called ion dipole forces and are essential in overcoming the ionic bonds within the lattice. Lattice dissociation. So as the water molecules surround the surface of the ionic solid, the ion dipole interactions weaken the electrostatic forces holding the lattice together. Eventually, individual ions are pulled away from the crystal lattice into a solution and they're broken down. Hydration. Once the ions are separated from the lattice, water molecule fully surround them, forming hydration shells. So once the sodium and chlorine are broken down, then the water molecule will surround them. A hydration shell consists of water molecule arranged around an ion with the opposite charge of the ion. For example, for Na, water's oxygen atom point toward the cation, while for Cl, water hydrogen atom point toward the anion. This hydration stabilizes the ions in solution, preventing them from recombining into a solid. Dispersion into solution. So after hydration, the individual ions disperse uniformly throughout the water, creating a homogeneous solution. The ionic compound is now fully dissolved. Real life example of ionic compound dissolving. So salt in water. When table salts NaCl dissolved in water, NaCl ions disperse, making the solution conductive. As you can see here, this is the Na sodium ion, which has been surrounded by the water molecule, while the Cl is also been surrounded by the water molecule. Dissolving polar molecules. In addition to ionic compound, water readily dissolves polar covalent molecules due to its ability to form dipole-dipole interactions and hydrogen bonds. Substances like sugars and alcohol contain polar functional group, hydroxyl groups that can interact with water. For example, when glucose dissolves in water, the hydroxyl group OH of the glucose from hydrogen bond with water molecules. So the water molecules surround the glucose, effectively dispersing it in the solution. This ability to dissolve polar molecules is essential for biological processes such as nutrient transport and cellular metabolism. Biological importance of water is a solvent. So water solvent properties are fundamental to life. In biological system, water acts as a medium. Usually we take water as a medium where countless chemical reactions occur and it serves as the transport system for neutron gases and waste products. In blood plasma, water dissolves ion like NaCl, nutrients, glucose, amino acids, and gases, oxygen and carbon dioxide for transport throughout the body. In cell, water is the primary component of the cytoplasm. Water also enables enzymatic activity, while also it maintains the osmotic balance, the pH regulation, and cellular signaling, etc. Solubility. Solubility is the maximum amount of solute substance solute that can be given in a given amount of solvent at specific temperature and pressure to form a homogeneous solution. One is called saturated solution, one is called unsaturated, one is called supersaturated. Saturated contains the maximum amount of solute, so maximum amount of solute that can be dissolved at a given temperature, while unsaturated contains less solute than the solvent can dissolve. And a supersaturated contains more solute than what can be dissolved under normal conditions. So we achieve the supersaturated by changing temperature and pressure. We increase the temperature and pressure, thus we can achieve supersaturated solutions. Factors affecting number one, temperature. For solid and liquid, solubility usually increases with temperature. For gases and liquid, solubility decreases. So for solid and liquid, it increases. For gases, it decreases. Pressure. Pressure affects only gases. Increasing pressure increases solubility in liquid. Nature of solid and liquid, solute and solvent. So like dissolve, like if they both are polar, they will be easily soluble in each other. Agitation and particle size. Stirring and breaking of solute into smaller pieces increases dissolution rate but not stability. Solubility curve. A solubility curve is a graph that shows the relation between solubility, amount of solute that can be dissolved, and temperature. It helps predict how much solute will dissolve in a solvent, typically water, at various temperature. Reading the solubility curve, the x-axis represents the temperature, while the y-axis represents the solubility. Each line on the graph represents a different solute. So above the curve, solution is supersaturated. On the curve, the solution is saturated, while below the curve, the solution is unsaturated. Types of solubility curves: solids and liquids. Most solids, KNO3 and NaCl, have solution that increases with temperature, while gases and liquid gases O2 and CO2 show decreasing solubility with rising temperature due to increases kinetic energy causing gas particles to escape. Solubility curves up H2O, KNO3 and H2O. So as you can see here, this region is supersaturated if the curve is on top. This region is saturated, and below this region is unsaturated. Common examples of such solubility detail: highly soluble substances. Table salt in water. About 36 grams of NaCl dissolved in water at 100 gram of water. At 100 gram of water at 25 degrees centigrade. Sugar in water. About 200 grams dissolved in 100. So that means sugar has got more solubility than NaCl. Slightly soluble substances. Now, calcium hydroxide CaOH2 forms a saturated solution known as lime water, 1.7 gram per 100 gram of water. Barium sulfate, very low solubility, 0.0000244 gram divided by 100 gram of water, but still dissolves slightly, important in medical imaging. Insoluble or practically insoluble. Sand in water does not dissolve due to strong covalent bond, and oil in water also does not dissolve due to molecules do not non-polar oil molecules do not interact with polar molecules. Gases, carbon dioxide and water. Used in carbonated drinks, solubility decreases with heat and causing soda to go flat when warm. Oxygen in water, essential for aquatic life but decreases with rising temperature, leading to oxygen depleted waters in summer. Main ways to express solution concentration. Number one is molarity. Number two is molality. There's not much difference between molarity and molality. Molarity is the number of moles of solute in 1 liter of solution. That means this is basically volume, moles divided by volume, moles divided by the liter. While molarity is basically the number of moles of solute per kilogram of solvent. So moles divided by per kilogram. So the only difference is the molarity is basically liter moles per liter, while the molarity is moles per kilogram of solvent. Key points: they are not affected by volumes, the molality, and changes due to temperature. Example is dissolving 1 mole of NaCl in 1 kilogram of water gives a 1 m NaCl. Number third is mass percent. What is mass percent now? Expresses concentration is the ratio of the mass of solute to the total mass of the solution multiplied by 100. Formula is mass W by W is equal to mass absolute divided by mass of solution times by 100, while volume percent is equal to the mass volume of solute divided by the total volume of solution expressed as a percentage. Number third is mass divided by volume, which is mass absolute in grams per 100 ml of solution. Now the percent W by V is equal to mass absolute per volume of solution ml times by 100, and parts per million ppm, parts per million, and parts per billion. Definition: this unit express very dilute solution concentration often used for environmental studies. ppm is equal to mass absolute divided by mass of solution times by 10 to the power 6, and parts per billion mass absolute divided by mass of solution times by 10 to the power 9. Uh, 1 ppm is equivalent to 1 gram per liter of water and common in measuring pollutants, pesticides, residues, or toxic metals. Example: 3 ppm leads to water means 3 mg of lead per liter of water.